Hello and welcome to today's webcast. My name is Brian and I will be your event specialist today. Following the presentation, we'll have a question and answer session. However, you can ask questions at any time during the presentation. Click the Ask a Question button, type your question in the open area, and click Ask Question to submit. We will answer as many questions as time allows. If you should need technical assistance, please type your inquiry in the tech support box on the left side of your screen and click the Send button. If you're disconnected from the webcast, you can log on again using the login instructions provided to you. If you cannot log back on with these instructions, please call support at 866-271-7592. It is now my pleasure to turn the webcast over to your speaker, Lee House. Lee, the floor is yours.
Very much. Okay, so the purpose of this webinar really is to give an introduction to GPU architecture to somewhat an OpenCL programmer's perspective. So my name's Lee Howes and I'm from AMD Sunnyvale. So what we want to do is look at the architecture using a slightly different approach from the normal, rather than just describing the architecture at the low level or describing optimizations for it. And those will be discussed later during a performance optimization webinar. We want to put the GPU architecture in context. So one problem we often see talking to people is that it can be hard to grasp why the GPU is designed the way it is and what its differences from CPUs really mean in context. And without understanding that, it can be quite hard to tell what types of algorithms are likely to run well on a GPU and why they're likely to run well. And so this means that you can choose the right tool for the job rather than wondering why your application does not go 100 times faster when you port it to the GPU naively. So the agenda for this webinar is first to talk about GPUs as graphics processors, i.e. their origins and their main use case. And this will lead to some discussion of the implications that has on the architecture, followed by some discussion of SIMD execution and its implications for application development. We'll then briefly discuss local memory and some aspects of latency hiding, processor state, and attempt to place the GPU in context with the wealth of CPU designs available with a couple of very simple examples. And the point of that is to show the GPU is not out there as a fundamentally different design. And then we'll end the discussion by discussing some of the specific features of the Radeon HD 5870 GPU. So we can start with what might seem the obvious question of what is a GPU? And looking at it from a compute programmer's perspective, it is at its heart a multi-core processor that happens to be tuned for processing pixels. So it has wide SIMD cores, which allow a high degree of data parallelism, where many pixels are processed together. And it has cores that are optimized for throughput, and we'll see what that means. And this is because traditional GPU pixel and vertex workloads show a high degree of independence of computation. The GPU core doesn't need the same low latency pipeline that a CPU designed for scalar processing requires. It also has optimized hardware blocks that are designed for accelerating a range of graphics-specific tasks. For example, the UVD block on the AMD devices, which accelerates video decode. And these features offer high performance for very specific workloads, but don't tend to offer the flexibility you might need for general-purpose computation, so most of this kind of work ignores them. So we can start from the beginning, really. Let's say we're processing pixel data. If we're processing data for a single pixel, we might have a light source defined in a buffer. We might have a color, a normal, some properties of the pixel. And we can read these values from memory or input registers and compute a value for how we want the light to affect the pixel, and this generates an output color. That much is simple enough. Of course, we can process multiple pixels together, and here on this slide we see the quad, the basic unit of most GPU processing. Of course, this quad is part of some polygon that was drawn to the screen by the rendering API. And the rasterization hardware will generate quads for the hardware to process based on the input stream of polygons that are being passed over by the DirectX or OpenGL runtime. So when we want to generate this output result, we're going to execute a fragment program, which will be written in a language such as GLSL or HLSL, depending on your graphics API choice. And in this case, we see some HLSL code. So what's important about this is that the program is written as if it's independent. So it relates just to a single pixel, with no notion at all of how these pixels appear together. And the output of the program depends only on the inputs that relate to that specific pixel, or at least some gather operation from the input buffers. And there's no interpixel communication. And so this is important because this allows the hardware to do very efficient parallelism with no dependence analysis. And the early general purpose GPU work was written in this fashion, using full screen polygons to generate large rectangular workloads. Sorry about that. Right. So as a slight aside, for each polygon we draw, we might be running a slightly different fragment program. And in this way, as well as having to execute vertex data, perform tessellation and so on, there's actually quite a high degree of programmatic or thread-level parallelism that the GPUs also have to deal with. And this also affects the design that we'll see. So that's the basic idea of what the GPU is doing. There's nothing complicated about that. But that pixel data is the major component of graphics workloads, and so that affects the way the hardware will be designed. So we saw our quad, and we saw that when writing graphics code, it makes sense to think in terms of a program for each pixel. And that's because, of course, it's the pixel we're generating data for, and that's the concept or the level that we're thinking at. And we usually don't have any real idea where on the screen that pixel will be or how it will relate to other pixels. The camera can move, the objects can move, and so on. So that means that data parallel execution at the hardware level is inferred from a dependence-free program or set of programs. Now, we know that each of these pixels can be executed independently, and hence in parallel. But at the same time, they're executing the same program, or at least small groups of them will be, because they're executing that same shader code. And we know that because the GPU's front-end rasterization and work scheduling hardware has generated a quad as 4 neighboring pixels from the same polygon. And in addition to that, it will make an effort to package quads from similar polygons or a single larger polygon together so that the same shader code is being executed. So the first thing we can see from this is that we can map these pixels to a SIMD engine. So that means that's single instruction, multiple data, in that the same instruction, the same program will be executed on all 4 pixels at once. So that's much like the SSE extensions to x86 processors. And on AMD's GPU hardware, this is known as a wavefront. Now, what this means is that we can get quite high ALU density. But the problem comes in when we have code that branches. So we have ostensibly separate programs that are now executing together on a single SIMD unit, which means they're all executing that single instruction. And as a result, that's a single vector instruction now covering all 4 programs. So for simplicity, I showed slightly different code here that has added some branches. Obviously, a clamp call would perform this same operation, but for the purposes of explanation, we'll keep the branches in. So the question is what's going to happen when we hit those branches. Now, if the branches all go the same way, this isn't a problem. If they don't, we might see the following sequence. So the first gather operation from memory will read the set of memory addresses for each pixel in a single instruction. And that's fine. All 4 of these pixel shader instances are executing together. And then we reach the if test. Now what this will actually do is this will generate a mask in hardware. Now if that mask is all going the same way, this might do a vector voting instruction and realize that and then turn into a branch. But if it doesn't, as we see on this slide, then because not all pixels have satisfied the test, we don't want them all to execute. But because this is a SIMD instruction, there is no way for them to not execute. The instruction will be issued for all 4 lanes. So what it will do is that mask that we computed will mask out the pixels that don't satisfy it. And so it will only output a result for those that do. And then when we reach the else condition, we're going to invert the mask. And the rest of the pixels will be covered by the following conditional assignment. And then the very last instruction will be the return statement, which will then execute again for all 4 lanes. So note that the shader that appeared to be 4 operations, a read, a test, an assignment, and a return, has become 6. A read, a test, a conditional assignment, inverting the test, a conditional assignment, and a return. And that's true for all 4 pixels in the quad, and indeed any pixels that have been grouped together over an entire 64-wide waveform. So note in particular the gaps in the execution trace. So these are places where the ALUs are being wasted, where SIMD lanes are executing instructions, but they're not writing useful results. And obviously, the larger those if and else blocks are, the deeper the nest of conditionals, the wider the wavefront, the greater the divergence between the computations occurring on different lanes, and the lower the utilization of the SIMD engine overall. And that means that we get less data parallel execution. And so the actual mean throughput of the hardware, while it can have a very, very high peak throughput, thanks to these wide SIMD engines and the efficiency that we'll discuss later, the realistic throughput will be a lot lower because of this divergence. So one thing that this brings up is whether SIMD execution requires SIMD instructions. So what we've done with pixel shaders, and this is why I've set this up as a gradual introduction from pixels, is that we've written a SIMD program without using vector instructions. The vector instructions can be generated either live by the hardware, as it just automatically masks, or by a compiler. So in the x86 world, people are used to using SSE intrinsics and the like, but the difficulty of thinking about those instructions can make development fiddly, and it becomes quite a skill. We have to think about manually packaging different operations to gather and scatter vector registers, and then we'll have to issue a gather or scatter instruction on that. And that means that we also have to manually perform branch masking, and we have to carefully hand code all of that. And with short vectors, that's possible. But with very wide vectors, true vector programming like that can be a bit of an art. So on the other hand, there is an advantage to writing vector instructions. So by programming this SIMD code lane-wise in this way, it has the risk of making the developer think that the lanes branch independently, think that each instance of the shader or OpenCL kernel branches independently. And while that can appear to be true, in the hardware it really isn't true. And so this is important to take into consideration if you want to achieve good performance. So while there's an argument either way, for wide SIMD hardware, it seems the lesser of two evils to program it lane-wise this way, because it's easier for the programmer to think about. For current AMD GPUs, the masking is controlled by hardware and is implicit in the intermediate language. So why does this matter for compute, which is really the purpose of this talk? Well, graphics code traditionally has relatively short shaders on quite large triangles, so this all gets less true with time. And so the level of branch divergence overall will not usually be very high. And it's also hard in those cases to control, because you don't have a clear idea of what pixels will be mapped to the same SIMD engine, because even if you know you have a large triangle, you don't know how close the camera will be to it. So you can work around the divergence, but you only have a limited amount of control over it. Whereas for OpenCL code, you're defining your execution space very precisely. You choose what work is performed by which work item and how that work item is placed in the grid relative to other work items. And so you can choose how to structure your algorithm to avoid this divergence. So what that really means is that if your code diverges in an OpenCL program, it's your fault. You've made a decision to leave it that way, and hopefully that's because it was appropriate for the algorithm. And later webinars in the series are better suited to explain what that kind of thing really means in terms of OpenCL optimizations. So the other primary visible aspects of GPU architectures based on my original claims are that they're for throughput computing. So the question is, what does this mean? Well, let's say we have a 4-wide SIMD vector that's executing instructions, and it stalls. Say it's waiting for the number of cycles it takes a floating point add to complete. Now, a fast-clocked, out-of-order CPU with very complicated control logic attempts to cover this stall with other instructions from the same instruction stream, hence out of order, and that don't depend on the output of the instruction in question. Or they forward data in the pipeline to reach the next instruction earlier than it would if it entered a register and had to be read again. And all of this requires very complicated hardware that occupies space, consumes power that could alternatively be diverted to ALUs. So the GPU takes a slightly different approach. First, on current architectures, we usually run a much wider vector over multiple cycles. And this means that we can reuse the same instruction to cover the stall time. So the time that the first quarter in the diagram of the vector is stalled for is covered by the second, third, and fourth quarters executing that same instruction. And this also has a benefit of reducing the instruction decode bandwidth. So it makes the stall much shorter once you view what the ALUs are then doing on those cycles. So on the 5870 GPU, we run a 64-wide vector on a 16-wide hardware SIMD unit, and that achieves this 4-cycle design. So what we actually see is that in this very simple example, we've completely covered the stalls. The ALUs are being kept busy, reaching 100% utilization. Of course, that was a very simple case. What if the stall's much longer? Say we're waiting for the return data from a memory request that can't be covered by the compiler inserting other instructions between the creation and use of the access. So even with our wide vector, there's going to be a gap. And we could execute a very wide vector. We could double the width of the vector in this diagram, and that would be enough. But there comes a point that you can make your vector wider and wider, but because of that SIMD branch divergence issue that we saw, that's just going to increase the inefficiency. It's going to reduce the utilization of the ALUs. And so that might not be the right solution. So the alternative that a throughput processor will use is that we can sneak in another instruction from another running thread. And in this case, I define a thread as a wavefront that's running on the same SIMD unit. So we can see that instruction 0 from the second thread has filled that gap between instruction 0 and 1 from the first. And the more wavefronts we have running on each SIMD unit, the more latency we can cover in this way. So if we have enough wavefronts running ALU instructions, we need never stall the SIMD unit waiting for the texture units to return memory data. Obviously, there'll be cases where that's just infeasible. But for the most part, you can get pretty close to doing that. What this means is that a single wavefront takes longer to execute. So instead of taking 4 cycles between the first instruction and the second instruction for the first quarter of the wavefront, it's now taken 8. more wavefronts you insert, the longer that gap becomes. But the whole point is that rather than trying to minimize the latency of execution of a single thread on the hardware, we're trying to maximize the throughput of a whole set of threads. And that means we try and increase the utilization, and we don't care how long it takes for the first one to finish. So the effect of that is that where we had a single SIMD engine, because we have many threads to cover that latency, we can feed in the next wavefront or another part of the wavefront on the next cycle, as shown here. And in turn, once we've obtained the results of whatever computation that first set of pixels were computing, we can feed those back in at the top. And we can repeat that with as many pixels as available to keep the pipeline as close to full occupancy as feasible. But what you should notice here is that we now have multiple pixels, all of them, while not actually in the ALU pipeline, they're sitting waiting to enter it. And you certainly don't want a delay before they're ready to enter. So that means we need to store state for each wavefront that's waiting to use the ALUs. So each thread in flight has to have its own set of register states covering any of the registers that it was using. And not only that, that set of registers has to cover the full width of the vector. So this register state takes up space on the device and will scale both with the number of state sets and the width of the vector. Now, the GPUs work by maintaining a large pool of registers that are just generically allocated for the state set based on the resource requirements of each wavefront. Now, most multi-threaded CPUs have multiple copies of a fairly precise architectural state set. So there tends to be a fixed maximum number. But that's just a quirk. The point is that the more wavefronts you want to fit on, the more thread parallelism, the more state sets you're going to need. So we don't care very much about latency because we have a throughput architecture. So this is another difference from the GPU to the CPU. Whereas the CPU wants to reduce the average access time for a memory read as much as possible. And the cache hierarchy is designed with that in mind. You want to read from the closest level of cache as much as possible because that has the fewest number of cycles and delay to return that value. And that's because you have a very small amount of state in there that you're trying to feed through with small latency. But because the GPU is already designed to cover latency, we can look at this from a slightly different point of view. We now are running a lot of threads. But because we have a lot of threads, they're accessing a lot of memory addresses. So rather than trying to minimize latency, we now have to maximize memory bandwidth available so that we can satisfy all that parallelism. So one approach is that GPUs use high bandwidth, high latency memory interfaces, such as GDDR. But even then, it's worth reducing the amount of data traffic because with that very large number of threads, the total amount of data required can be very large. So that is where texture caches and local memory come in. So both of these are really intended to support the reuse of data between work items. Hence, on our architecture, the local memory regions are called the local data share. So that's to say they support spatial locality, but less so temporal locality. So these caches and programmer-controlled shared memory regions achieve data transfer reductions by allowing data to be copied just once over the main memory interface and then reused by different work items in varying patterns. So the texture cache is particularly designed for this in that it can automatically enforce 2D structure on its data to efficiently capture 2D accesses by those quads and by the fact that on any given polygon, the pixels are likely to be accessing closely related data from the input buffers. With the local data regions, we have considerably more control, and like structuring the branches with the SIMD, it's the developer's responsibility to structure loads to efficiently use this memory and to share data to reduce the global memory requirements. So another benefit of this local memory over a cache is that it can be built much more efficiently in the cache because it does not have the need for tag lookups and management structures that are needed for automated caching. So for the same number of transistors, higher capacity and bandwidth are both possible. So you will remember that I said earlier that each SIMD unit shares a single instruction fetch and decode block. So by sharing this hardware among multiple ALUs in SIMD fashion, we minimize the amount of silicon consumed by control logic. And while these fetch and decode steps stay relatively fixed in size, as we increase the number of state sets, we increase the size of the execute block at the bottom of this diagram, and that is dedicating more silicon to computation where it's useful. So in this case, we have a much, much larger block. And we can do that because not only can we scale the SIMD engine up, we can also increase the number of state sets. So the vertical dimension of this is really the amount of state in the system. And horizontally is the number of ALUs, the width of the SIMD vector. And that means, so we're getting much more reuse out of the fetch and decode units. And that's why the current GPUs have very wide SIMD engines with a lot of state sets. But the amount of both so not only does the amount of register state grow, but also the amount of local storage and cache will need to grow. So there is still going to be some trade-off based on the amount of non-ALU hardware on the chip that has to be traded off against the amount of threading you can do. But there does come a point where the pure data parallelism is no longer adequate. So as we saw earlier, not all polygons need to run the same fragment program, and particularly when we're doing compute code, if we carefully design the code, knowing how it's going to branch, say we have each work group branch a different way, then there's no problem with branch divergence because those sets of code are completely independent. What that means is that we can then reach a point where we have multiple cores on the hardware. So depending on the workload, a design with narrower SIMD cores and more of them might be more efficient. For programs with a high degree of dependence and control flow, maybe an architecture that doesn't rely on very wide SIMD might be better. And the maximum ALU density would be achieved with one enormous SIMD unit executing a single instruction stream, but that would have no latency hiding. So each state set or core you add decreases the ALU density, but with the benefit of increasing utilization of the ALUs. And where that trade-off falls depends very much on the workload. And the trade-off falls the way it does with the GPU because we have graphics workloads that are very parallel. So this is essentially what the general-purpose compute parallel programmer can view a GPU as, a collection of wide SIMD cores, each one carrying multiple program states and interleaving 4, 8, 16 threads to cover pipeline latency. And so that means that we can think about putting the GPU in the design space of the CPU core designs that are available. because the reality is that GPU design is not completely different in some abstract sense. It relates to this design space, and it's just a point where the trade-off has fallen a certain way. So these examples are a slight simplification, but they should give the general idea. So, for example, the AMD Phenom 2 X6, 6 cores, that's well known. Each one has a single state set per core. There's a single hardware thread running on each core, and each one uses 4 wide SIMD. In reality, we have multiple SIMD and integer pipelines, but let's keep things simple. So Intel's i7 takes a very slightly different approach, and the Pentium 4 did something similar, where we now have a slightly larger core, but it contains 2 state sets, so that they can interleave instructions that are executing on different ALUs simultaneously on the same core. And so that helps increase the amount of instruction level parallelism available, rather than just trying to extract it from a long instruction sequence. But that does come at the cost of more complicated control hardware. Sun took an interesting approach on this with the UltraSpark T2, or Niagara 2, and the original Niagara similarly. And that has 8 cores with 8 state sets per core. It doesn't have SIMD, because that was designed for scalar web processing workloads. So it forgoes data parallelism entirely in favor of a high degree of thread parallelism. And so then, of course, the AMD GPU design. So you could argue this is at the extreme end of the spectrum, which is what we'd expect given the very high degree of data parallelism in GPU workloads. So competing GPUs on the market choose fairly similar design points. NVIDIA's GTX 480, for example, has 15 cores and 16 wide SIMD, similarly large number of state sets, slightly different implementation of how it extracts instruction level parallelism. But the general point in the design space is relatively similar. So if we looked at the question of whether the GPU and CPU designs would converge, ignoring putting them on the same die with fusion, but really converge, really what we have to ask is what the workloads are and how those are best executed. And the current CPU workloads just don't execute that well on GPUs, and the same is true in reverse. And until they come together, the designs are always going to be different points in the design space. So what I want to do now is run over some of the technical details of a particular GPU implementation. This is the AMD Radeon HD 5870. From a compute programmer's point of view, most of the same details apply to devices further down the hierarchy and into the 6000 generation. So, as a general summary, it's a 2.72 teraflop architecture at absolute peak in single precision, and a little under 550 gigaflops double precision in 2.15 billion transistors. So, note in particular the the 2,560 bytes a clock of LDS bandwidth, which is about 2.1 terabytes a second. And that's twice as high as the L1 bandwidth because of what I said earlier about the higher efficiency of designing a programmer addressable shared memory compared with cache. And it's an order of magnitude higher than external bandwidth. And the number of concurrent wavefronts on the device peaks at 496. But that's based on the number that the scheduling hardware can deal with. The reality is that the number of concurrent wavefronts will depend on how many registers each wavefront uses out of that 5.24 megabytes of vector general purpose registers, and indeed out of the 640K of local data share, which are both divided up among wavefronts and workgroups depending on the requirements of each kernel. So this diagram gives us a high-level view of the GPU. So when a kernel is dispatched, the command processor at the top will decode it and generate some number of wavefronts to run the device, or indeed will generate quads which it will package together if it's processing and rasterizing pixel data. If a SIMD unit has free resources and a full workgroup occupies few enough resources to fit in that space, it will be assigned to that SIMD. So the entire chip has 20 SIMD engines, which is arguably 20 cores by comparison to CPUs, with 8 GDDR5 memory banks for crossbars and read caches. And in addition, there are write combining caches and read-write caches which are used for global memory atomics. So one important design feature is that it follows a relaxed global memory consistency model, which requires fence instructions to ensure visibility of writes, unlike the x86 designs, which are largely coherent. And that ensures that the SIMD engines and text units can maintain a high degree of data parallel execution as possible without the power and performance overhead of coherency mechanisms. So one unusual feature is that the hardware has a clause-based execution model, which you'll see whenever you look at ISA code in the stream kernel analyzer. So the green code on here is control flow code, and that will be executed by the two sequencer units at the top of the chip. Each of these units interleaves control flow programs from all of the threads. So between them, they will interleave the control flow that's up to 496 wavefronts that we saw. So in the first line of the example is an ALU clause start instruction, which means that the sequencer will execute that instruction by dispatching the contents of that clause to whatever SIMD unit the current wavefront has its state living on. And then we'll see that SIMD unit will execute the clause while the sequencer goes away executing control flow code from other wavefronts. And the other SIMD units will be executing clauses of their own. At the end of the clause, a predication value has been generated that the sequencer can use to continue control flow. And here it's then executing a jump instruction, which may mean it has to generate a branch mask. It may actually do a branch, depending on how the vote of that predication goes. And this branch generation, the mask generation, will then be automatic in the hardware. When it reaches a texture clause, that will be farmed off to the memory controller and the texture units rather than to a SIMD engine. And while that data fetch is executing, other clauses from other control flow programs can be executing on the SIMD engines. And that increases the amount of parallel execution possible on the device and helps with covering latency. And the overhead of that is minimal if there is a large number of clauses available to execute. But it can become significant if your program does not contain much thread-level parallelism, i.e. you have not issued enough wavefronts to occupy the device. And so it's an important aspect in carefully tuning the code for peak performance that you look at these blocks of ISA code and just get some idea of how the code is likely to perform. So on that diagram, we saw those 20 SIMD engines. This is a simplified diagram of a SIMD engine. It contains 16 processing elements that make up the physical vector in hardware. And these will execute a single instruction in an ALU clause across a wavefront for over four consecutive, well, not 4 consecutive cycles, but every other cycle of a block of 8. And so each wavefront in an application sits on a given SIMD engine. That's where all its register and LDS data is maintained. So this data isn't being moved about because that would be inefficient. And each SIMD engine can execute wavefronts from multiple kernels simultaneously and interleaving two wavefronts from separate clauses over those 8 instructions. And lanes in the SIMD engine will, of course, be enabled and disabled to support masking, as we discussed. So within the SIMD engine block here, there are 2 major components useful for compute programs. The first is the local data share, which allows sharing of data between work items in a work group. And the other is the processing element, or sometimes confusingly known as a stream core. And this executes instructions from ALU clauses in the kernel. As I said, there are 16 of these, and we'll briefly discuss these over the next few slides. And I will go back a slide again for you. Right. So the local data share composes 32 banks, and each of the 16 processing elements in the SIMD engine can request to read or write 2 32-bit words from LDS on each cycle at arbitrary addresses, or at least the reads are at arbitrary addresses. The writes, thanks to the number of slots in an instruction, can be at a base address and a stride. In the case of conflicts on LDS banks, the unit will detect the conflict and reissue the read or write over subsequent cycles until all requests have completed. Atomic operations are performed using this row of small integer-only ALUs associated with each bank near the bottom of the diagram. And in that way, non-returning LDS atomics are processed entirely within the LDS, independent of further execution in the SIMD engine. That enables very high instruction throughput for code with a large number of atomic operations. And because locking and everything else is very efficient when it's done directly in the LDS system, it does mean that floating point atomics would be more complicated to do. So the LDS has a much higher bandwidth that can be produced to external memory. It's more compact, more efficient than cache, as I said. As a result, each SIMD can achieve 1 kilobit per clock cycle with a single instruction latency for indirect reads. And of course, a single instruction latency doesn't mean 1 cycle. It actually means 8 cycles. And all of this can be pipelined through the LDS system. So this is another example of throughput execution in action. So we can cover that 8-cycle latency comfortably by the time the next instruction might arrive. So the other feature of the SIMD engine is the processing element. So the processing element of the 5870 architecture is a cluster of 5 ALUs that operate on a very long instruction word, or VLIW, packet of instructions. What this means is that rather than executing a single instruction, the unit executes a single instruction packet of 5 operations that have been packaged by the compiler with some set of known dependencies. So 4 of the ALUs are identical and can execute basically any 32-bit floating point operation, or they can be combined to execute more complicated ones. The 5th ALU is also capable of executing most of the basic operations, but in addition contains a special function unit that can generate sine and cosine and so on. The VLIW design means that the compiler has to generate packets of instructions to fully utilize the device. But in moving this work to the compiler, the hardware can very densely pack ALUs. Again, we're trading off, we're moving for high peak throughput by reducing the amount of control hardware that's necessary. So that's why the design has a very, very high peak. But of course, you'll never quite achieve that because you'll never get 100% packing. And again, this can be seen in the ISA code. When we saw the code list before, we saw this X, Y, ZWT set of 5 operations. And you can tell at a glance that your loops aren't unrolled, for example, enough, because you see that you only see X's, and then you're not getting very high packing. And the analyzer tools will give clues see this next? Yeah, it took a while to return the next slide to me. So one of the features is it can co-issue certain sets of dependence operations in a single packet. And so this helps increase the amount of packing the compiler can do. It doesn't have to be 5 completely independent operations. So, for example, a .4 could be issued that is, of course, it has to do the adding operations between the lanes. But that can be issued as a single packet. Each lane can also do a 24-bit integer operation, though to do 32-bit integer multiplies, they have to be combined. And there are different ways that the lanes can be combined that the compiler knows about. So the final feature, which is a lesser-known feature, is the global data share. I didn't mention this initially, but it was shown on the large diagram. And as you can see, this doesn't look significantly different from the local data share. It's 64K in size, twice the size of the LDS, and the general functionality is the same. The important thing about this is that it's connected to the entire set of SIMD engines on the device. Now, it's not fully exposed as a memory in OpenCL or indeed in DirectX, but the way it is exposed in DirectX at the moment, and you can imagine exposure in OpenCL, is that it supports fast append counters. And so the append buffer feature that is visible in DirectX, which allows you to create compacted output data sets with optional output from each work item, is accelerated using this. So these features allow acceleration of specific constructs, even though they might not be available as a general purpose memory. So that offers 25 clock cycles latency, so it's far lower latency than accesses to DRAM, and can deal with 8 work item requests per clock cycle. So that was just a brief introduction to the hardware. We can answer some questions if you have any, or maybe you've asked some already. So in summary, we've looked at the basic principles of GPU architecture in the context of the processor design space, and I hope that for some of you at least gives a slightly different point of view on the design. We've seen some of the trade-offs that lead to GPU features. And we've gone over the basic features of the 5870 architecture that affect compute applications. But later talks will actually go into detail on GPU optimizations and the architecture, the way these architecture features are really used. So now we can answer a few questions. The first question: can the cores access random pixels in the texture cache? Will that cause performance issues? They can access random pixels. It will cause performance issues in that if the reads are clustered together, either as a cache line. I mean, you can think about aligned operations on the CPU in a similar way. If you bridge 2 cache lines, then it will have to do 2 reads, and the texture cache is the same. It will be faster than doing global memory accesses, though, of course, because any parts that do fall in a cache line can be read immediately. And then it will depend on the banking of the cache structures, precisely how those will be fed to the ALUs from the cache, in much the same way as the LDS, but more automated. So the next question: are the special functions or transcendentals for the 5th ALU the native versions of the OpenCL functions or the full precision ones. Those would be the native versions if the native functions in OpenCL are generating them. The full precision, so those transcendental functions generated by that fifth lane are not full precision. They're a fast approximation that is good enough for the majority of graphics code, and it may or may not be good enough for compute code depending on your needs. So actual full precision would have to execute a longer instruction sequence. So what's the best way to obtain full occupancy? For example, should work groups consist of multiples of 16 work items, 64 work items, etc.? That's a complicated question that I think we'll probably go into more detail in a later webinar. Certainly, the immediate thing that's brought up in the question, they should consist of multiples of 64 work items. If they were only multiples of 16, say there were 32 in a group, you would only ever get 50% occupancy. That would be like a branch that masked off half of your wavefront. So that would definitely be bad. What the actual full occupancy of the system will depend on is not so much the size of the groups, but the number of wavefronts that can fit on each core. So if your groups are very large and they don't have too many barriers in them that obviously cause stalls by design, then the larger group will have more wavefronts. But if the group's too large, then you might not be able to fit two, and so half of the core might not be utilized. So fitting smaller groups might pack better. But independent of that, if each wavefront has too many registers used, then you won't be able to fit many wavefronts on it. If each wavefront or each workgroup requires too much local memory, then you won't be able to fit them. So it really depends on a whole set of factors based on how many registers you're using, how much local memory, how big your groups are, for actual efficiency, how many barriers you're using, how much branch divergence there is, and so on. So it is a complicated question, really. So there is a question about the Radeon 6000 series, and so I should say that at the moment I can't really say anything. Certainly I can't say anything about the cards that have not been made public. The Bart's card, the 58, the 6870 that is already public, is very similar in most ways to the 5000 series evergreen cards. From the point of view of compute, there are no significant differences to think about. In the rest of the hardware, there are significant differences. The video decode block, for example, has been improved a lot. But from a compute point of view, there's nothing too significant to think about. Is there a way to query the wavefront size of OpenCL devices? No, not really. There is a query that will get you the preferred workgroup multiple, I think, in OpenCL 1.1, which our runtime, as far as I'm aware, does return 64 for. But of course, you know it's 64 for our hardware anyway. The question is whether everyone's hardware would return that correctly, if that's the question you're asking, and there's no guarantee of that. You can, of course, do some sort of lookup table on the different devices that you might be running on. So, could you explain what fully coalesced means? So this would refer to global memory accesses. And what it would really mean, in the simplest case, is that your quarter wavefront that's going to issue a memory request in one go will be accessing float or 4 vectors from each lane, so 128 bits from each lane, at consecutive aligned addresses going across the SIMD unit, because that's the absolute peak for memory accesses. There are then levels of fall-off efficiency if that's not aligned, or if that's a random gather, and then that all depends on whether it's a cached access or not a cached access. So at that point, the actual performance hit becomes complicated. But in the simplest case, that's what fully coalesced would mean. So this is a good question. In case then I wasn't very clear earlier. Someone's asking what exactly I mean by a wavefront. So just to clarify that, a wavefront is 64 work items in simple terms. What it means in terms of the hardware is that it is the unit of work that is executed as a SIMD chunk. So there is a single instruction that is executed over those 64 work items. So they will branch together. They will do everything together, unless they're masked out. But even then, they will still execute through the ALU and just not write anything. That's subtly different from the hardware vector, which will execute that 64 work items by running it over 4 different cycles. But that's what a wavefront is. It's the logical SIMD vector. Let's see, I think we have time for 1 or 2 more questions. So yes, the wavefront is the equivalent of NVIDIA's warp. It is basically the same thing. If the kernel needs many registers, will different workgroups still switch to hide latency? Meaning the register contents must be shifted in and out of RAM, or will the kernel run to completion so the register contents are never stored in RAM? With the current designs, the hardware will not automatically shift registers to RAM. A workgroup will run to completion on a core, and this is why you can't guarantee global synchronization between all workgroups in a dispatch, and why global synchronization is not recommended, because you have no control over which workgroups are actually on the device at any given time. However, if your kernel does use a very large number of registers, the compiler can generate operations that move that register data into private memory, which is sitting in DRAM, and then back again. This is known as a spill. And in that way, the compiler can reduce the number of registers that kernel requires. But the hardware won't automatically spill and return. So one last question. In OpenCL speak, is a wavefront a workgroup? No. A workgroup is a set of, a workgroup is a set of work items. If you're programming efficiently, the wavefront will be one or more, the workgroup will be one or more wavefronts. That is, it will be one or more sets of 64 work items. So you want your workgroup to be a multiple of 64. So your workgroup might only be one wavefront in size. Many OpenCL programs I've written are designed that way. But it might be more. And if you have more than one, then when you issue a barrier instruction, your synchronization will then be between those multiple wavefronts. If you only have one wavefront in your workgroup, then barriers don't mean anything. They will be reduced in non-operations